My name is Paul Holes, Applications Engineer for Anritsu, EMEA Limited, working for an engineering and technology team across EMEA. So I've been working with Anritsu for just over 30 years now, looking after test and measurement equipment, starting from service and then going into the application and support side post-purchase. So today's session is about interference hunting and how we differentiate between different types of tools to look for interference, and the differences between some of those products that we have and the different types of interference that we encounter. The agenda here is we're going to discover the problem of interference, what types of interferences there are, how to mitigate that interference via either spectrum monitoring or clearing, some signal identification techniques, and interference location finding. And then, as I said, a chat between the difference between a spectrum analyzer, signal analyzer, and a real-time spectrum analyzer, some tools that we use in our interference hunt, and then an example on using a real-time spectrum analyzer to examine a 5G carrier. And then finally, a recording about some of the everyday interference issues that we encounter in the ISM band. So this is sub 3 gigahertz band, where we have lots of common devices that can cause interference in that particular band in our household and everyday life. So the wireless challenge, what is the wireless challenge? Well, the spectrum's becoming much more crowded with more transmitters, more mobile devices, as stationary transmitters are no longer the norm. We have new modulation types, with analog signals becoming less common than digital signals, and more complex modulation schemes. And with a higher audio modulation, it requires a better RF environment. We also have spectrum refarming, where moving services to different frequencies requires spectrum clearing and involves different propagation and interference types. And wireless connectivity has moved from a nice to have to a must have, particularly since the epidemic over the last couple of years, where many more people have been working from home and connecting with each other wirelessly. So the problem with interference and the need for clear spectrum, well, there's only a finite usable spectrum available, and usage is strictly controlled. And currently we have a situation where frequency resource is limited and there is only a certain amount of spectrum available, and being able to use that spectrum is strictly controlled and enforced by regulatory authorities from kilohertz all the way up to 300 gigahertz. And it's important to control to avoid clashes and people using spectrum they haven't paid for. And therefore it's very expensive to obtain and protect their allocation of frequency band. Some particular example and something we encounter daily is the UHF band, 300 megahertz to 3 gigahertz. And you can see here that even this small section of the frequency bands is full of different types of communications, which are always evolving too. So it's very important that the operators look after their bands and keep them clean from sources of interference. So now we can talk a while about sources of interference and what kind of things can interrupt our communication systems. We can characterize these into two groups. Random sources are devices which unintentionally generate RF signals, and common sources are things like electric motors, faulty transformers, vehicle ignition systems, electrical fences, fluorescent lighting, etc. And typically fairly easy to recognize and often show up as jumps in the noise floor or a wide random spectral pattern. Intentional sources include cellular repeaters or bidirectional amplifiers, or BDAs, which can be used to extend cellular coverage in buildings or in fringe areas. And they can also be installed on boats. And the main interference issues here are the retransmission of unwanted signals at the input of the BDA, as well as malfunctioning BDAs, which it presents as noise. And these are difficult to troubleshoot, but a very common source of interference in the cellular bands. Jammers are typically easy to identify and locate, as they are generally a strong signal, broad, and tend to increase the noise floor even outside of their nominal operating range. And also there's deliberate interference, which may be narrowband, i.e. talking on a public safety frequency, or broadband, known as jamming. There's also pirate or unlicensed operations can also cause issues to licensed users. And these sources may be mobile, possibly to avoid detection or radio location. And although most businesses and individuals are very cooperative in resolving interference, deliberate interferers will usually deny or conceal their activities. Another source of interference is passive intermodulation. So what is passive intermodulation? Well, it's the simplest definition is that it's interference. And PIM is new frequencies generated by the transmit signals at a cell site when they interact with nonlinear elements in the RF path. In an ideal system, the transmit signals pass through the RF infrastructure and no new frequencies are generated. When nonlinearities are present, however, many new frequencies, here shown in blue, are generated at mathematical combinations of the transmit frequencies. And if these new frequencies fall in the uplink band, they can raise the noise floor, causing high drop call rates, access failures, and slower data rates. So what is a nonlinear junction? Well, when we say nonlinear, we are talking about the relationship between current and voltage at metal junctions. And examples of linear junctions would be high contact pressure, metal-to-metal connections, soldered or welded connections. And as the voltage increases across these connections, we get a linear increase in current across the junction. Nonlinear junctions occur when there is low contact pressure, oxide films, or misaligned surfaces. And in this case, we get a nonlinear relationship between current and voltage that behaves like a diode. This is the building block for a mixer. And when these nonlinearities are excited by high power RF signals, mixing occurs and PIM frequencies will be generated. What does that look like at a cell site? Well, in the field, most PIM problems occur at metal-to-metal connections. And PIM can be caused by poor preparation of the coaxial cable where it interfaces to the connector body, metal flakes left over by the cutting process, or loose rivets. And all of these result in loose metal-to-metal contacts in locations with very high RF current density. PIM can be both inside the antenna system and beyond the antenna, with rusty metal surfaces or non-linear materials such as nickel, steel, and ferrite. So now we'll go through different steps of interference mitigation. In mitigating interference, there's typically 3 stages: spectrum monitoring or clearing, signal identification, and interference location finding. So let's begin with spectrum monitoring and clearing. So why do we need to do it? Well, we need to understand the RF environment to enable us to spot when something has changed. And when something has changed, when something changes, we have some general information about the frequency, the timings, and the amplitude. And how do we do that? Well, we have key performance indicators, and we have RF tools which limit notification capacity, such as spectrum analyzers and associated equipment colleagues. So signal identification. How do we spot and characterize interference? Well, we check for the interference at the receiver, and then we check at the tower for cellular or the complaint area for a two-way, or in the complaint area for broadcast. And we allow the receiver pre-filter to eliminate strong side emissions. And we measure the noise floor from a receive antenna, which should be the same receive pattern as the radio. Here we get a visual ID on the interference signal, and then we should characterize the signal so we know it later. And here's an example of one of our filters that connects to our interference hunter, which I'll talk a little bit about later. So once we look at the receive frequencies, the signal passed by the radio's receive filter or the pre-selector after the receiver's front end causes a reduction in sensitivity or apparent low C over I or carrier to interference ratio. This is called receiver desensitization, or block-in if it's very severe. The thing to remember is the interference signals do not need to be on your receive channel. They only need to make it through the receive filter. And a real example of this technique is a public safety organization in northern Nevada was experiencing intermittent receive interference alarms on its 800 megahertz P25 public safety communication system. And an ordinary tuned spectrum analyzer was used in an attempt to locate the interference signals. However, none were found. And after determining it was not a software issue, it was decided that the cause of the issue was likely to be an interference signal with short duration or even a hop-in signal that was missed by the spectrum analyzer. And a spectrum analyzer with real-time spectrum analysis, or an RTSA, was needed to be utilized to look for any interference signals. When performing interference testing in multi-transmitter locations like this, it is not uncommon to see a 0 dBm signal levels at the front end of a spectrum analyzer using a standard whip antenna. The interference signals that were being hunted on the system could be as small as -110 dBm. And a 0 dBm signal at any frequency within the analyzer's front end range would prevent detecting these small signals, as the input attenuation required to prevent front end overload would result in a consequent high noise floor. And several measurement techniques were employed to ensure all interference would be located quickly and accurately. The first action was to perform a survey of the overall site spectrum environment, and we're using a broadband whip antenna, which provided coverage from 500 megahertz to 3 gigs, connected to the unit, the spectrum from 9 kilohertz to 1 gigahertz with 30 dBs input attenuation was observed. The P25 transmitter suffering from intermittent interference can clearly be seen around 800 megs. To reduce the television and FM broadcast power incident at the instrument RF input, a high-pass filter was inserted between the antenna and the RF input. And this will enable the use of less input attenuation in the amplifier, in the analyzer. Switching the spectrum analyzer input attenuator by ±5 dBs, it was confirmed that no change in the measured signals was seen. This is a common technique to validate no overload of the analyzer RF front end, showing that with a high-pass filter on the RF input, it eliminates the high-power FM transmitter signals. And next, the Fieldmaster Pro 2090A was connected to the system receiver test port with an 800 MHz bandpass filter, plus the high-pass filter to further isolate the P25 signal. And this allowed the analyzer to have the same sensitivity as the P25 receive system. With the Fieldmaster Pro put into RTSA mode and markers were set on the system's 4 receive frequencies. This verified that incoming traffic could be seen, and initially in RTSA mode, both real-time and spectrogram views were used to try to catch briefing interference signals. And this facilitated monitoring for correlation between wanted signal traffic and potential interfering products. And when no interference was present, the activation of P25 traffic is clearly seen as dark lines in the spectrogram. Occasionally, the entire noise floor would jump up to -60 dBm above the incoming P25 signal level. And this was captured as dark horizontal lines in the spectrogram trace that covered the full P25 spectrum. The Fieldmaster Pro has a probability of intercept as low as 2.05 microseconds, so that even these very short duration bursts of interference were captured. The dark horizontal lines in the spectrogram trace highlight short bursts of high interference signals that covered the full P25 frequency plan. These interference signals had a power level in excess of -60 dBm, which is greater than the wanted P25 signals. And when the 2090A was switched to standard spectrum analyzer mode to capture traces with and without interference to understand the level of the increasing noise floor. This shows the analyzer noise floor when no interference was present, and the sensitivity of -110 dBm is in line with typical P25 radio's performance. In standard spectrum analyzer mode, it's necessary to use the trace max hold feature to build up an image of the noise resulting from the bursts of interference. And since it was established that there was interference on site, a directional antenna was attached to the Fieldmaster Pro in order to walk the site to hone in on the exact source of interference. And often periodic antennas are used for direction finding as they offer wide frequency coverage. However, the directional pattern is a compromise compared to Yagi antennas. Direction finding antennas may need to have a low PIM specification to prevent the antennas from generating interference signals on their own from the very high RF fields present at broadcast sites. When direction finding, it is best to start with the antenna aimed towards the ground to see the spectrum display with little interference, and then bring the antenna to horizontal and slowly rotate 360 degrees. Rotate the antenna from vertical to horizontal to see if there is a peak in the polarization. In this case, the signal peaked when aimed at a broadcast tower, and it was not polarization sensitive. And there were, however, numerous metal buildings in the area, and it needed to be confirmed that the direction was not from a reflection. Walking around the tower at a 30-meter distance, the direction finding was repeated, and in all cases, the interference maximum was with the antenna pointed towards the tower, and levels increased further when the antenna was aimed towards the top of the tower. Using this technique, the noise interference was determined to come from a broadcast tower located 50 meters from the P25 antennas. And this mountaintop tower supported a number of broadcast transmitters with numerous antennas, so the RF fields close to the tower were very high up. After experiencing significant winter weather, it was discovered that a safety climbing cable running from the ground to the very top of the tower had broken away from its insulated mounts. And with high wind, this caused the cable to bang up against the tower, causing passive intermodulation, or PIM, and set off alarms in the P25 receiver monitoring system. It's well documented that incidental contact by movement between dissimilar metal conductors that are physically and electrically close to transmitter antennas and high RF fields will result in passive intermodulation products and cause erratic impulse noise on receivers near the site. And during a return visit to the site at a later date when there was no wind, it was noted that there were no alarms triggered in the P25 monitoring system. And so when hunting for interference, reflection from buildings and vehicles can cause multipath and erroneous direction readings. So it's best to take direct readings from a number of vantage points to be sure of the source of the interference. And there were two hilltops at this site. When retesting from a hilltop 1 kilometre away from the shared P25 and broadcast tower site, the only interference source came from the direction of the P25 and broadcast site, providing further evidence that the true cause of the interference had been identified. And where other solutions had failed, the Fieldmaster Pro 2090A, with its real-time spectrum analyzer option, was able to detect the source of an intermittent interference signal at an 800 MHz P25 communication site. And with the RTSA, it has spans available up to 110 MHz and a 2.05 microseconds POI. The Fieldmaster Pro provides a capability for broadcast FM, land mobile radio, cellular, and full ISM band interference monitoring, making it the ultimate signal analysis and interference capture tool. So in the previous example, it wasn't necessarily necessary to have a deeper analysis of the kind of signal we were hunting for, but there are many occasions when it's required. For example, is it a repetitive signal? Does it repeat often, or is it a random signal? Or does it have a common pattern or a typical modulation type or scheme? And post-processing tools enable us to get deeper insights of the type of interference or signal that we're trying to find. So here's a few screenshots of some captured RF environments. Is there any interference here? One of these is a snapshot of the FM transmitters, but which ones may be not so regular or authorized? And we need to understand our RF environment. I always say if you can't see it, you won't find it. We need to know and understand what we are looking for. Here is a snapshot of Wi-Fi activity. We'll talk more about this type of interference on this band a little bit later. So now on to interference location finding. Why do we do it? Well, obviously it's the final step in removal of the interfering source. And we need to do it if the signal source is unknown or hidden. We do it when the interference on a particular site is confirmed. And we do it via directional tracking of power using various different tools. So what tools do we need to be able to locate these sorts of interference? Well, we have different types of spectrum analyzer. We have a real-time spectrum analyzer, a normal swept-tuned spectrum analyzer, and a vector signal analyzer. Spectrum analyzers are the fundamental instrument used by RF engineers to measure individual signals across a defined frequency band. They capture and display wanted and unwanted signals, enabling a range of measurements including power, frequency, modulation, and distortion. There are several different types of spectrum analyzer system architectures. First of these is a swept-tuned spectrum analyzer. A swept-tuned spectrum analyzer scans the input by sweeping its local oscillator to down-convert the input frequency range to a fixed intermediate frequency, or IF. This is then filtered by the resolution bandwidth filter and detected. And as the local oscillator is swept, the input signal frequencies are effectively swept past the fixed frequency resolution bandwidth filter. In effect, the spectrum analyzer can only see a small portion of the frequency span at any single moment, and therefore the signal is visible only when it appears at the resolution bandwidth filter, at the right time and frequency. And it's blind to transient signals that appear when the sweep is scanning a different part of the input frequency range. And here is an example of that. If the red line is crossing a signal, you see it on the display. The spectrum analyzer is missing any signal during its sweep revisit time. This is called the blind time. Increasing the sweep speed is resulting in a higher number of signal crossings, but nevertheless, there is always a revisit time and therefore a SPA blind time. It's a swept LO with an assigned resolution bandwidth, and it covers a much wider span than an RTSA, and it's good for events that are stable in the frequency domain. However, it's magnitude only. There is no phase information on the signals that you're seeing on a traditional spectrum analyzer. And it captures only events that occur at the right time and the right frequency point. And data information is lost when the local oscillator is not there. And you can see here, there is a correlation between the sweep speed, the span, and the resolution bandwidth. So as you narrow the resolution bandwidth, there is a trade-off in time. The time swept increases. Therefore, low-level bursty or transient signals are difficult to see with a traditional spectrum analyzer because the signal may appear and disappear by the time the spectrum analyzer sweeps through it. The next type of spectrum analyzer is a vector signal analyzer. So with a vector signal analyzer, this down converts the signal of interest within a certain bandwidth to a fixed frequency IF. The IF analog signal is then sampled by an analog to digital converter, and a stream of time domain samples can be used for modulation domain analysis. For spectrum analysis, the time domain samples are transformed into a frequency domain spectrum using the fast Fourier transform, or FFT. And the FFT processes a block of samples, which will be referred to as a sample frame. The number of samples in the sample frame is referred to as the sample frame size, or FFT size. And when the FFT calculation is finished and the results are transferred to the display, the next sample frame is acquired. And although the LO is stationary, unlike the swept spectrum analyzer, the vector signal analyzer is blind to signal events occurring in the time gap between sample frames. And nearly all modern spectrum analyzers combine the features of both the traditional swept spectrum analyzer and a vector signal analyzer, the Anritsu MS2830, 40 or 50 series. If the span is greater than the FFT analysis bandwidth, the local oscillator will be stepped along to stitch together multiple FFTs to display a spectrum with the desired span. And what sets an RTSA, or real-time spectrum analyzer, apart is its ability to continuously acquire samples of the signal and perform FFT analysis. And this slide illustrates the difference. So for non-RTSA spectrum analyzers or vector signal analyzers using FFT analysis have a serial process flow to acquire samples and calculate the FFT. The RTSA process flow is parallel in that it can acquire a new sample frame while simultaneously performing the FFT on the previous sample frame. And this parallel processing requires fast digital hardware and a large memory buffer. The Anritsu Fieldmaster Pro is capable of performing 527,000 FFTs per second for a 512-point FFT. And the number of points of an FFT is the number of frequency points that span the FFT analysis bandwidth. And it's also equal to the number of IQ samples collected in a sample frame. And the more points, the finer the frequency resolution. And however, the FFT computation time increases. The key performance metric is the probability of intercept, or POI, defined as the minimum signal duration necessary to accurately measure the amplitude of a continuously wave signal. And the POI is affected by several factors: FFT processing speed, sample rate, window overlap, resolution bandwidth, and span. So with the Fieldmaster Pro capable of completing a 512-point FFT at 527,000 times per second, this is much greater than the LCD display update rate, and a density display is used to show the measurement results in a meaningful way. And the density display shows the color graded intensity of a signal event, and the warmer the color, the more frequent is the signal event. The density display can also simultaneously show up to 6 spectrum traces, and the spectrum traces represent the detection result for all the FFTs calculated during the acquisition interval. The peak and negative peak detection selects respectively the maximum or minimum amplitude level detected for each frequency point. And in sample detection, the trace values represent the amplitudes from one single FFT acquired during the acquisition interval. So what kind of things do we have in our interference hunting toolbox? Well, there's various methods available: walk-in and drive tests, directional scanners, TDOA triangulation, and audio tones. And to interference hunt, I said earlier you needed to be able to see what you were looking for. And in that end, the 2090A Fieldmaster Pro is the highest performing handheld spectrum analyzer on the marketplace today. And there's various models available from 9 kHz to 54 GHz. Has a very fast sweep speed and a low displayed average noise level, coupled with an incredibly good phase noise, allows you to see signals amongst larger signals because it isn't hidden underneath the skirt of the internal noise of the spectrum analyzer. And with 110 MHz real-time spectrum analyzer bandwidth, gives us a POI of 2.06 microseconds and 5 nanoseconds minimum detectable signal. A POI of 2.06 microseconds means that any pulse signal with a duration of 2.06 microseconds or greater, the spectrum analyzer will be able to see it and capture at full amplitude accuracy and 100% probability. So in reality, the instrument can see and capture signals of smaller duration, but perhaps with a reduced amplitude accuracy. However, sometimes this doesn't really matter, because once you've found the signal, you can change the settings on the analyzer further to diagnose the road signal more thoroughly. The point being, as I said earlier, you need to be able to see it to do something with it. The unit also has a 40 MHz resolution bandwidth in zero span mode, which is very useful for narrow pulse analysis. And a recent addition is the IQ streaming and capture option. And this means that in the field, you can capture up to 110 MHz of IQ data, which is fully flexible in terms of going wider and narrower, and up to 2 GB of RAM, which enable you to store those captures. We also have an interference finder option. This provides audio tone response to changes in interference levels, and also some further options added to this. We have polar displays too. The Fieldmaster Pro is also fully compatible with our mobile interference hunter vehicle solution and our remote spectrum monitor vision software. We'll talk a little bit about this in the next few slides. So as you need to go deeper into the noise floor, you need to decrease your resolution bandwidth, and subsequently the sweep time increases. So to be able to look at low-level sources of interference, you need to be able to sweep quickly at low levels across a wide frequency range. We have save an event facility where the unit will save the date each time it crosses a predefined limit line or a set of complex limit lines, and also it's useful to be able to have multiple markers and multiple traces. And for example, rolling averages and max hold, etc., all displayed simultaneously on the same display. And as we've already discussed, the RTSA is very useful in that because of its architecture, we can see signals that would normally be hidden beneath the trace of a conventional spectrum analyzer, and it allows us to track fast-moving or sporadic signals that would otherwise be challenging to find. And if we add the spectrogram dual trace feature, we can also track them over time, as shown here in the bottom display. The Vision Monitor software options 0400 and 0407 offer a range of applications for monitoring the RF spectrum over a period of time and storing results to a database. The Vision Monitor is an ideal tool for long-term interference monitoring. Limits can be set with automated alarms of limit violations to capture short-term or intermittent signals, and other features include a scanner option that enables the monitoring of a range of frequency bands with unique settings for each channel being monitored. We also have the Interference Hunter, or MIH. So this is the system uses a power on arrival application and gradually builds up a picture of the power for a particular source in different environments. And as you drive around, it recalculates where the likely source is to be found, leaving a trail of breadcrumbs which are color coded dependent on the power measured. See here. It creates a histogram, and you can go back to relevant positions. Once close to the source, you can utilize the handheld interference hunter to find the exact location. The Fieldmaster Pro's fast sweep speed also supports use with the Anritsu PIM Hunter probe. In cases where PIM is causing an issue with signal integrity, this PIM probe can be connected to the Fieldmaster Pro MS2090A and used to pinpoint the precise location of the PIM source. The analyzer is tuned to the frequency of the modulation pulse tone, PIM tone, and the signal output decreases dramatically as the probe tip gets closer to the source. So basically here you create your two tones with the PIM master, and that creates the IM product, and connecting the PIM probe and use that to touch around suspected sources of PIM. These could be rusty nails or bolts, etc., and show right at the start of this presentation. So now a closer look at a 5G carrier. So here there are two representations showing the same 5G carrier over a wide span of 110 megahertz, with an automatic scaling on the left-hand side and the manual scaling on the right-hand side. Sometimes using a manual scale with a preferred density scale top value will help to show evidence of some behaviors of the carrier. And here we see the same frequency carrier, but with the bottom scale above 0%. This is actually 0.5% here. In other words, we can say that this would help to eliminate the RTSA representation, every signal which will not be present more than 0.5% of the time. And in this example, this clearly helps to see the SSB synchronization blocks, which is located in the middle of the span. And since the persistence duration is variable, we can use it to determine which frequencies are present in the 5G carrier. So if you set the persistence to 0 milliseconds, your eyes may not have enough time to see the representation on the display, as the FFT processing on the 2098 is incredibly fast here. Here in green is the max hold trace, and the orange trace is what has been measured over the last 53 milliseconds. And this information is shown on the bottom right of the screen. The orange plot is nice to show the envelope of the 5G carrier without having to do anything special in the RTSA. When you're making 5G carrier measurements, you can never be sure that there will be any data communication or not. By now, as networks are under deployment in EMEA, and there are not so many 5G mobiles on the market with subscribers that would require a high data rate. So here we show the 5G carrier with or without the data packet communication. The vertical scales are not exactly the same, but you can immediately see the activity using the RTSA. So the next part of the presentation will highlight features of the RTSA that facilitate observation of frequency hopping interference signals and how Wi-Fi and Bluetooth technologies adapt their activity to minimize interference. The 802.11 standard defines 14 channels in the 2.4 gigahertz band, but each channel is typically about 20 megahertz wide. And in practice, it's only possible to have 3 or 4 non-overlapping channels. The access points continuously transmit beacon signals so that users can find and connect to their networks. The standard allows for some flexibility, but these beacon packets are typically transmitted every 100 milliseconds and have a duration of a few milliseconds. In this demonstration, I used the RTSA feature of the 2090A to analyze Bluetooth and 802.11 Wi-Fi signals in the 2.4 GHz ISM band. And this will highlight features of the RTSA that facilitate observation of frequency hopping interference signals and how Wi-Fi and Bluetooth technologies adapt their activity to minimize interference.
So let's have a look at some of these signals using the RTSA on the MS2090A Fieldmaster Pro. So here I've just set up the 2090 spectrum analyzer in normal spectrum analyzer mode to look at the ISM band between 2.4 and 2.5 gigs. I've got 2 traces here, one in clear and write mode and the other one in max hold mode, which is the green display. As you can see, it's quite difficult to see the Wi-Fi access point very clearly using this method. You can see that it's there, but you can't really see what's going on. So now I go into RTSA mode, you can see the Wi-Fi access points quite clearly over the whole of the ISM band. So now I'm going to bring a Bluetooth phone near to the antenna and we'll see what happens. So what happens is when a Bluetooth low energy device is active in the area, it transmits packets on 3 advertising channels at a fixed frequency. So now I've brought a Bluetooth speaker nearby, and what it does is it will create a fast scanning raster of defined frequencies when you bring a Bluetooth device near. There it is. And now I'm streaming the audio music from the Bluetooth speaker, and you can see the constant activity on the display of the real-time spectrum analyzer. Now I'm turning the Wi-Fi on the phone, and it's sweeping the full spectrum, looking for beacon packets from the access point. And here, by changing the persistence, I can see the Wi-Fi access point quite clearly, even though it's a lower level signal than the Bluetooth. Just here. And now I've just got hold of a microwave oven, and I'm going to turn that on, and we'll have a look and see what happens. So it's clear from here that there's a significant interference signal leaking from this product, and this typically results in significant dropping of the Bluetooth or the Wi-Fi throughput, or even complete communications failure.
So in conclusion, having a high-performance portable spectrum analyzer like the 2090A is essential for detailed analysis of crowded areas of spectrum. With a probability of intercept of less than 5 microseconds means the MS-2090A RTSA is certain to capture the shortest of packets seen in the ISM bands. The spectrogram feature provides a view over time of spectral RF activity, and a usable settable persistence mode enables identification of signal within signal interferers. And when associated with other tools and accessories, the RTSA is an invaluable instrument when interference hunting in the field.